In this video I will compare the airspy with its Spyverter with the SDRplay, both of them on 14 MHz. I'm feeding both radios from this unit. It's a 3-port hybrid splitter. The third port goes to a spectrum analyzer. The signal comes from here. This is a 20 dB directional coupler. The signal going straight through is 2 tones, and then the 20 dB suppressed signal that is added is a reference signal that I will show how to use later. The reference signal, it's on 14050 plus 100 Hz. The two strong signals, this one and that one, they are set to produce exactly the same signal level in the test objects. I switch them off and check the spectrum analyzer, and hopefully it can be seen that the level here is 85.6 or 85.5. The cable loss is 0.15 dB from here to the hybrid, so that is something I neglect because the accuracy of this instrument is maybe 1 dB or so. The signal, the reference signal, is far too strong. It looks like this in the airspy, and we have it here, or like that, in the SDR the SDRplay. So I will reduce the signal significantly. It's now minus 90, and the audio output from the airspy, you can see the noise is much higher. The signal to noise ratio here is reasonable for the measurement of noise figures. And you can see in the airspy we have the signal here, not very strong. And likewise in the SDRplay, the signal is here, and the noise floor, you can see how it has increased very much. So now we can measure signal to noise ratios and get the noise figure. I'm using lean rod to monitor the output from the airspy. And I have set the bandwidth to 500 Hz. So I have the noise plus the signal here. I can evaluate it and find 89.6. And then I will move the frequency a little bit to get a little bit outside the signal, like that. And then I have to wait a little bit to be able to see what is now the noise floor. 82.3. 82.3 means about 7.3 dB S plus N over N for the airspy. And then I do the same for the SDRplay. And here I also have lean rod monitoring the audio output. And I click on the side. First I evaluate what the level is, 99.1, and then move the frequency to place the signal outside the filter, like that. And you can see, obviously, the noise figure is much lower now for the SDRplay as compared to the airspy. The noise floor is 77.8. So here is what I've got. The signal to noise ratio is 6.4 dB, converting from signals plus noise over noise to only signal over noise, get this result. While when S plus N is much larger than N, there is no difference. To get the noise figure, I take the signal level, which is minus 115.7. I looked a little bit longer on the analyzer. The noise floor in 500 Hz bandwidth is minus 147 dBm. That's Boltzmann's constant times the bandwidth. It means for a noise figure of 0, I would see S over N 31.3 dB. What I see is 21.3 for the SDRplay, means noise figure 10. And for the airspy, I get the noise figure 24.9. It's unfair, of course, to compare these receivers that are so different in sensitivity. For 14 MHz, a noise figure of 10 dB is too good. 25 is reasonable, but I think the appropriate comparison should be with the preamp switched off in the SDRplay. Then the noise figure will be even a little bit higher than 25. I will have a look at that. I don't want S plus N over N very small, so I step up the level here by 10 dB. And then I go to the SDRplay and switch off the preamplifier. That's here, LNA, off. And then I look at the noise figure. First, we have the noise floor. I have to wait a little bit for that. We are just above the signal now. The noise floor is 84.6. And I wait for the signal level. And S plus N over N is 95.97, well, 96.0. It's not fair to the SDRplay to run it without any gain reduction in what comes after the LNA. So I turn on some gain reduction here. Until I see some loss in S over N. This could be an appropriate point to operate this unit when comparing the dynamic range with the airspy, which I will set then for the same noise figure as we have here. So again, I evaluate the noise figure. I will make it a little bit faster. It's not necessary to get very high precision. So okay, from here to here then. So S plus N is 94.8. 85.8. That's the noise floor. So, without the LNA and with 10 dB more signal, I have S minus 105.7, means I would have 41.3 dB signal to noise ratio if the noise figure were 0. What I have measured is noise 84.6, signal plus noise 96, means S plus N over N is 11.4 and S over N is 11.1. So compare that to 41.3 and I get a noise figure of 30.2. But it's unfair to do the comparison with the full gain of the tuner. I mean, what is inside the SDRplay is an up converter and an ordinary VHF and UHF tuner. So with some gain reduction, as you saw, I observed these numbers and the noise figure now is 32.8. And I will set the airspy for the same noise figure. To reduce the gain and to get the appropriate noise figure, first I set the gain mode to linearity. We are not looking for optimum sensitivity. This is to test the linearity, the intermodulation. And then I turn down the gain until I see that I lose some noise figure. Maybe something like that. I want to lose 7 dB. And then I look in the S meter graph and I change the scale so I can see directly. I want 9 dB here, and this was far too much, so I decrease gain a little bit more. And here you can see the noise doesn't go down anymore, but the signal does. And then, so 81, I want it to go up to 90. This is about right. We were there, 81.1. To 90.4. This is accurate enough for what I'm going to do. I have set the generators now 1, respectively 2 megahertz below the signal frequency on 14.05. And I have moved the cable from the spectrum analyzer to a Perseus. And this is what I see near the signal frequency. Attenuate the 2 strong signals by 10 dB. So this is no good. It's necessary to do a different setup. Now I have again the generators 1 megahertz apart, but there is no attenuator. They go directly into the hybrid combiner, and then a 10 dB attenuator followed by a notch filter. This notch filter has a notch that is about 80 decibels deep on 18493, that's where the minimum is. And then the attenuators and into the different receivers. What I see on the Perseus, which is still connected, is like this. I turn up the level in steps of 10 dB. 1, 2, 3, 4, here is the intermodulation. It's 50 Hertz away, and then 10 dB more, and it doesn't increase much, just a little, and again 10 dB, and it happens to go down. This is typical for digital feedback. A weak signal on the frequency of third order intermodulation that goes up and down. 10 dB more, and it became weaker again. Another 10 dB, now it's stronger. Another 10 dB, now it's really strong. So we are approaching some real nonlinearity in the passives. But you can see the SDR-play, it's totally saturated, and also the airspy. So now the setup is okay, and I will start doing some dynamic range measurements. Linrad can be set to display signal-to-noise ratios. If you declare you're an expert and enable the second FFT, you get the option to get S over N here. What is measured is the power of the waterfall, the entire waterfall, and compared with the signal that passes through the baseband filter, the filter here. I have set the bandwidth to be exactly the same for the two systems. The airspy, the lower corner frequency, I can click on it here, and you can see that the 3 dB point is very close to 100 Hertz. And for the SDR-play, it is, well, 85. So I move it up 1 pixel like that. And now it's very close to 100 Hertz also. And the upper edge here, 2400. It's about a 3 dB point. And here, the upper edge, 2400. So the power, the noise floor is computed from the same bandwidth in both radios. And the noise floor is very flat. If it were not, I would have to take that into account also. The baseband filter is set with the same sampling speed, 12 kilohertz, the same FFT size, and I have made the 6th pixel 10 dB below the flat range. It's here, and 10 dB below that, and of course the same here. I have switched off the weak generator, so there is only noise now in the baseband. So what I measure is the ratio between the noise power here and the noise power here. And that's essentially the bandwidth ratio with an unknown calibration factor on it. So I read it out here and get 35.58. And feed that into this calibration window, 35.58. Next time I do the measurement, I should get signal to noise ratio 0, because there is no signal. And then the same for the SDR-play. $35.21. It should be exactly the same. 35.51. And I think it is. I don't remember what I said on the previous. And now I read here minus 0.3. Well, this is a noisy signal, so there differences from time to time. But this seems to be systematically wrong. I may have entered something incorrect. Happens occasionally. I do it again. 35.27. 35.27. And now we get 0. And the other one was 35.58. So there is a 0.3 dB error of unknown origin. I switch on the weak signal. And make sure I have it at the center of the passband here. And here it is already at the passband center. So I have to wait for a while. So I check here. The signal to noise ratio in the airspy is 20.7. Then the SDRplay. 20.0. I changed the gain reduction from 74 dB to 73 dB. And you can see it goes up a little bit. And now the SDRplay is 20.4. Maybe one more step upwards here. 72. .65. That's close enough. Now the noise figure is the same for both radios, and it's time to look at the effect of sending in the strong signal. The generators are separated by 1 megahertz. And I introduce the strong signal now by increasing the signal with the attenuator 10 dB at a time. 1, 2, 3, 4. You can see here the signal is coming. 5. Oops. Here there is a big loss and there is a big intermodulation. So I back off one step. And we have about 3 dB loss in the signal to noise ratio. It means that a signal level of minus 25.8 dBm is the strongest signal we can have before losing 3 dB signal to noise ratio. And here is the airspy. We have now 1.5 dB loss. 1 dB, 3 dB loss, 1 more dB, 5 dB loss. So this is the level we can have, and you can see the phenomenon is the intermodulation. That's what gives this 3 dB loss. The main spectrum does not look ugly in any way. You can see here in the SDRplay at this signal level the loss is only half a dB. The level into the airspy is minus 28.8 dBm. Now the separation is 200 kilohertz between the strong signals, and I look at the airspy. and the degradation I see now is 2 dB, so I increase the level 1 more dB, and we have too much. So here is the level, and it is 41.8, minus 41.8 dBm. In the airspy, the loss is now 2 dB. I step it up the level. One more. Something like this. We have a 3 dB loss. It is noise to a large extent. It is not so much the third order intermodulation. And this is what the main spectrum looks like. And here in the airspy. And the level for the SDRplay is minus 39.8 dBm. Now the separation is 20 kilohertz. And here is the airspy, the main spectrum, and the signal to noise ratio. It is degraded by 4 dB, so I reduced the signal 1 step, that's 1 dB. And now the degradation is only 2 dB. And the level here is minus 41.8. And here is the SDRplay. And the level for 3 dB loss is minus 44.8 dBm. As you can see, there is some spur. So I switch off one of the strong generators, the one at 14.16. Intermodulation goes away, but the spur not. So I switch that back on, and then I switch off the other one at 14.14, and then the spur disappears. So there is also a weak spur that is not significant, I think. Here is the result of the comparison between the SDRplay and the airspy. The maximum signal level, as you just have seen, is here. The noise figure is set to 32.8, as you have seen, the same for both radios. The minimum discernible signal at 500 Hz bandwidth is room temperature 174 dBm, plus the noise figure, plus 27 dB for 500 Hz. That's minus 114.2 dBm. So I get the dynamic range by subtracting the maximum signal level from the noise floor, and I get these values. At wide range, the SDRplay is about 3 dB better. At close range, the airspy is 3 dB better. At wide range, the SDRplay has a little better linearity. At close range, the airspy has less noise. I give numbers here with decimals. Don't get confused. I don't mean that the noise figure is 32.8. There is some uncertainty. Not so small uncertainty, but when comparing the results, then it becomes meaningful. So the differences are close to 3 dB with the decimal 0. I think these radios are pretty similar. Maybe your preferences on software should govern which one to buy or use. Maybe the possibility to add a preamplifier in the SDRplay could be important. On the other hand, in the airspy, you can add a 10 MHz reference to lock the frequency to GPS or something. The Spyverter cannot be locked to GPS, not the current version, but I think there will be a new one that can be locked to GPS. Now I have replaced the two strong signals with a signal from an antenna, and it's amplified quite a bit, but there is also an attenuator after the amplifiers. I have reduced the bandwidth of the IF in both the SDRplay and the airspy to 500 Hz. That is to match the notch filter, because the notch filter is inserted after the amplifiers and before the signal is split into the two radios. And I have set the gain to get the same signal to noise ratio, like here and here, 25.5 on both places. And now I turn on more antenna signal. Oops, here there is a problem. This was too much. I have to back off in 1 dB steps. Here is roughly what the airspy can tolerate. And you can see for the SDRplay it is rather similar. You can see here the notch, and if I turn up the antenna signal, at this point the signal is completely destroyed. So what I find is that there is a small difference between these radios, 2 or maybe 3 dB, and the antenna signal I have now, it looks like this. There are many signals at around minus 32 or 35 dB, or maybe even more. But I'm running these receivers now for difficult circumstances. That means in the case of the SDRplay, I have set the bandwidth here of 0.5 MHz. If I make it wider, let's say 2 MHz, I expect more signal to go into the AD converter, and it is likely that it would saturate earlier. Although it doesn't seem like that. I try 1 MHz. And it's about the same. I go for 5 MHz. And that seems to be a little bit worse. But it's not very critical. The corresponding in the airspy, it's the decimation here, because that controls the filter. I'm sampling at 10 megahertz. That provides some oversampling advantage. It reduces the noise level by 6 dB in the AD converter. So I changed the decimator rate, go like that, and that's not good, because now we have more signal into the AD converter because the bandwidth is larger. So if I have the full bandwidth, then of course everything gets saturated. That's 10 megahertz. 5 megahertz is not okay either. So I think the conclusion is there is no very big difference between these radios. I have now increased the gain to get a better noise figure. And you can see here, I don't remember the previous, but I think this is something like 5 dB better sensitivity. And I have set the same for the SDRplay. And the settings required for this is I had to switch on the LNA and also add quite a lot of gain reduction, 71 dB in total gain reduction. And now things are different. I turn up the antenna signal. Oops. Here there is a significant loss in the SDRplay. And of course it varies a little bit time because all the stations are not constant in amplitude. But you can see there is severe interference now. In the airspy there is no problem yet. I add 1, 2, 3, 4, so something like 4 dB better. It's not a big difference, well, maybe 5 dB. Six dB. Well, now it's certainly no good anymore. 5 dB. So this is a close to real life test, setting the narrowest IF bandwidth and listening for a weak signal in a crowded band.